All right, this is Unit 7.8. It's the last one in Unit 7. We're going to be talking about exponential growth and decay models. There are a bunch of different types of examples. I'm only going to run through 3 examples of exponential growth and decay. There's also a thing which is called the logistic model. I'm going to basically explain what it is, but we're not actually going to do an example on that one. So I'm going to try and make sure I remove any of that stuff from your homework if it's in there. You'll actually get much more logistic stuff if and when you go into calculus, but that's actually not even until Calc 2, so I don't think it's worth our time to go through it right now. It's good to know about, but it's not something you have to worry about doing for problems right now. Okay, exponential growth and decay. You're going to find that it's going to be very simple, very similar, definitely not simple, very similar to what we were doing with interest. Very, very similar kind of formulas. The natural growth model looks very similar. Natural growth. The equation is a of t, not a times t, that's a of t, it's a function, equals a sub 0, sometimes said a naught, like N-A-U-G-H-T, probably sounds more like N-O-T, but it's not N-A-U-G-H-T, I believe, e to the kt. And you might look at that, and hopefully you're saying, well, wait a minute, if the a sub 0 was p and the k was r, it would look just like continuous compound interest. And it does. And it's exactly the same formula. We just changed some of the letters because now it's a different application. Other than that, it's exactly the same thing. This isn't interest. This is going to be an exponential growth or decay based upon most stuff in real life, so life sciences. So that's the only thing. So this is basically, and don't write this as P, but that's basically the same as P, and that K value is the same as your interest rate. They are basically the same thing. So I'm going to get rid of those. But that's what you need to understand. All right, our first example is going to be based upon bacteria growth. This is an extremely common example of exponential growth and decay. Bacteria grow at a very, very fast rate because of exponential growth and decay. And this is actually how they grow, so this will fit. So we're going to be given an equation. And your book actually uses N. I'm not really sure why. I would personally use B for bacteria, but it doesn't make any difference. So they're using N of T for our bacterial growth. And that's going to be equal to 100 e to the 0.045 T. N is basically the number of grams of bacteria. So N represents the number of grams of bacteria. Not the actual number of bacteria, the number of grams of bacteria. Okay. So we're going to do a bunch of different parts. Part A, determine the initial amount of bacteria. I do apologize for all the writing on this one. B, what is the growth rate of the bacteria? C, what is the population after 5 days? D is going to be a D and an E. How long will it take for the population to reach 140 grams? And letter E, what is the doubling time for the population? Whoa, that was weird. All right, a bunch of parts to this one. Fortunately, there won't be nearly that many parts to some of the other ones that we do. All right, so the first thing says, determine the initial amount of bacteria. If you want to figure out what the initial amount of bacteria is, that's the very first thing that you start with. You can probably see it from this if you understand what I said before, that A sub 0 is basically like your principal. It's the starting amount. If you didn't know this, the way to figure it out for letter A would be, okay, well, the initial time means it's at time 0. It hasn't started yet. So if I simply take t to be 0 and plug 0 into my equation, then I get n of 0 equals 100 e to the 0.045 times 0. And times 0 means that, okay, 0.05 times 0 is 0 in the exponent. Remember that e to the 0, or any number to the 0, is 1. So that equals 100 times 1, or 100. That's your initial population. Okay, again, we probably could have figured that out if we just simply realized that that was basically the same as your principal as before, as the initial amount. It's the amount of the investment, however you want to think about it. This is the initial population. That's what the A sub 0 represents. Letter B, what is the growth rate? Again, remember that K is your growth rate. It's the same thing as the interest rate. This is just not interest. It's how something grows. It's given as a decimal. So we know that K is 0.045, but as an actual percentage, as a rate, now instead of having the decimal and having to divide by 100, we have to multiply it by 100 so that we can actually get a percentage out of this. So the growth rate, multiplying 0.045 times 100, is going to give you 4.5%. And that's your growth rate. Part C, what is the population after 5 days? This is probably the easiest one because 5 represents the time. We plug 5 in for t. So that's going to be n of 5 equals 100 e to the 0.045 times 5. That's supposed to be an e down there. There we go. And then you just plug that into your calculator, literally. So you'll do 100 times e raised to the 0.045 times 5. Just make sure you do the whole 0.045 times 5 in the exponent. And let's see, you should end up with 125.2 grams after 5 days. So it is, after 5 days, it has grown 25.2 grams. I'm going to have to slide this down a little bit to fit D and E on here. D and E are going to, oops, this is supposed to be a different color. D and E are going to take a little bit more work. So D says, how long will it take for the population to reach 140 grams? The question is, how long? They're asking us to solve for T. We're solving for a time. And they want the population to reach 140 grams. So that's going to go in, the 140 is going to go in for N. It's going to go in for the N of T. So it's going to be 140 equals 100 e to the 0.045 t, because I don't know what t is. That's what we're solving for. But we do know we want the new population to be 140. So, got to do a little bit of work. Now to solve for t, we have to divide both sides by 100 in order to isolate the exponential equation. And then we're going to take the natural log of both sides of the equation so that we can eventually get that t out of the exponent. So we'll take the natural log. If you want to, you can certainly simplify 140 over 100, or you can just leave it for purposes of this because you're just going to plug in your calculator at the end anyway. Don't start plugging this stuff into your calculator as you go and rounding, because then your answer is going to end up wrong at the end. Because if you keep rounding every single time you have to plug something else in, it's going to round wrong at the end. So then we'll take the natural log of the right-hand side. If you remember from before, when I bring the exponent out to the front and multiply it, the natural log of e is 1. So all I'm going to have left over is that 0.05t. It saves me one extra step if you realize that's what's going to happen. So we'll have the natural log of 140 over 100 equals 0.045t. Again, please don't just scratch out the ln of e and say, oh, they cancel each other out. That's not what's happening. We're just saving an extra step by bringing the exponent out to the front and realizing the natural log of e is 1. So I don't have to write that part. Now to solve for t, I'm going to divide everything by 0.045. So t is then going to be the natural log of 140 over 100, all divided by 0.045. Again, that doesn't have much meaning to anybody, so we'll plug that into the calculator. Be very careful plugging it in. Make sure you end your parentheses in the correct places. And the time here should work out to be approximately 7.5 days. So it's going to take 7.5 days from for the population of bacteria to go from 100 grams to 140 grams. And then part E, I'm going to put that over here, I believe was how long it was going to take for it to double. Yeah. What is the doubling time? So we're doing exactly the same process. We now want it to double. Well, they actually gave us an amount this time, which was the 100 initial population. So, of course, 200 is doubling. You don't really have to put that stuff in. Probably better here just so you don't make any little mistakes. Oops, that's not a negative. Not sure what's going on here with my pen. Hold on. So now we'll divide both sides by 100. And here we end up with our 2. And that's going to equal e to the 0.045t. Once again, we'll take the natural log of both sides. And then, again, bring the 0.045t out to the front. Remember, natural log of e is 1, so we're going to get the natural log of 2 equals 0.045t. And then to solve for t, we divide by 0.045 on both sides, which is going to be t equals natural log of 2 over 0.045, which as a decimal, it should be longer than 7.5 days since it didn't actually double in the previous part D. It only went up to 140 in 7.5 days, so I would expect that this will be more than 7.5. We plug that in the calculator. You get 15.4 days. You write that 15 a little bit better. My 5s look horrible on here, and I apologize. They look bad as it is, but it's even worse when this thing kind of drags when I'm writing. So 15.4 days. Okay. All right, because of the time that these take, I'm actually only going to do one more problem. The other one was just another example that was very similar to that one. So I think as long as you're okay with that, Again, you can go back and watch it as many times as you need to kind of understand what's going on there. No need for me to go through a separate example on that one. I do want to do one, and this is kind of a cool thing. This is something they actually do in real life, especially, what do they call them, that people that go looking for archaeologists. That's what I was looking for. Archaeologists actually do this so they can date things that they found. They actually use what's called carbon dating, and that the process is actually done this way. So we're going to start off again with our equation. A of t equals a sub 0 e to the kt. We're going to be told that we find some kind of an item, whatever it is, somebody's digging around someplace, wherever they go exploring, and it's got approximately 1.67% of its original amount left. If we are told the half-life of carbon-14, carbon-14 is approximately 5,730 years. Approximately when was this original thing found, or when was this original thing there? So let me try and explain what I mean by this, because the wording on this, I know my explanation hasn't been really good. First of all, half-life. Supposed to be in green. Come on, give me green. There we go. Half-life means it takes 5,730 years for carbon-14 to deteriorate to half of its original amount. So if something has carbon on it, then what you can tell is how old it is based upon the fact that it takes 5,730 years to deteriorate to half of what it was. Okay, how they found that number out, I'm not really sure, but I do know that that's the half-life for anything that's got carbon on it. It takes that long to deteriorate to half of its original amount. What we're being told is we've got some kind of a substance which has 1.67% of the original amount of carbon left on it. So it's deteriorated quite a bit. We're trying to figure out how old this thing actually is based upon that information. So what we're going to do is we're going to say, okay, what I know is that A of t equals a sub 0 e to the some growth rate, or in this case, a decay rate, and I don't know what that is. But what I do know is that it's going to take 5,730 years, 5,730 years to get to half of the original amount. So I don't care what the amount is. Let's put any amount that we want to in there. Let's make things easy for ourselves. Let's do a nice easy number like 10. Again, this doesn't matter. But what I do know is that if I'm going to get half of that in the amount of time that was given, well, half of that would be 5. Now the question is, why am I doing all this? I'm doing all this because I need to find K. I need to find the exponential decay rate. I have to get that in order to be able to use that information to find what I'm actually looking for, which is to figure out how much 1.67% of something is. So we're going to go ahead and solve this for K. We're going to divide both sides by 10, which, not a surprise, is going to give me half on the left side because it's half of the amount. It's the half-life. E to the K times 5,730. All right, I don't have anything to isolate. The e is already isolated on the right, so I can use the natural log procedure that we did before. So it'll be the natural log on both sides, so the natural log of a half equals the natural log of e to the k times 5,730. The right side, left side stays the same. The right side, bring the k times 5,730 out to the front. Natural log of e is 1, so what we end up with over here is k times 5,730. So my k value, dividing by what's in that parentheses, is going to be the natural log of 1/2 divided by 5,730. Again, you could get a decimal approximation. At this point, I'm not going to worry about that because I need to use this k value to go ahead and solve the rest of the problem. I think maybe in your book they might actually go ahead and show you what the decimal is, but I prefer not to do that at this point in time. What I do know is that what we are looking for now is for the total amount, which is the amount on the left-hand side, to be 1.6% of its original value. Well, remember that's a percent. We have to turn it into a decimal. So you're going to divide by 100, which is 0.0167. So what we've got is 0.0167. That's the new amount of stuff. Whatever it was, again, we don't know how much stuff there was. We just know that's the new amount. Well, that's going to equal e to the, now I do have a k value, which is the natural log of 1/2 divided by 5,730 times t. We are solving for t. We are trying to see, based upon the fact that we found the decay rate, which was k, how long it's going to take to get to 1.6% of its original amount. I am willing to bet this number is going to be quite large, considering that is way over half of its life. But let's find out. So we'll do the same process. We'll take the natural log of 0.0167, which is going to equal the natural log of e to the ln of 1/2 divided by 5,730 times t. The entire exponent comes out to the front. Natural log of e is 1. So you get the natural log 0.0167 equals natural log of 1/2 over 5,730 times t. And then this part's going to be a little messy. I'm going to multiply both sides by 5,730. Try and make it a little less messy. And then we're going to divide both sides by the natural log of 1/2 to get t. So t is going to equal 5,730 natural log of 0.0167 all divided by natural log of 1/2. Again, that's your exact answer. It really doesn't mean anything to anybody. So at this point, we will plug this into our calculators. And we come out with the fact that this is 33,830 years. Write that a little bit better. 830 years. That's a long time. So whatever this artifact was that now has exactly 1.6% of its carbon left, it's 33,830 years old. That's a long time. There's another application which is called Newton's Law of Cooling. That is also something that you will learn in Calc 2 if and when you get to that class. It's actually a really cool thing. Cooling, cool, yeah. But not something that we need to spend the time on. Last topic I'm going to talk about, I'll get this done in less than 5 minutes because this video is running long, was this thing called the logistic model. It basically is something that kind of follows exponential growth and decay to a certain point, But because of some kind of limiting factors in nature or something else, it tends to level itself off. So what an exponential growth model looks like graphically, if you remember, exponential growth, when it starts down here, whatever it starts at, tends to grow very, very fast for a while. And then exponential growth just keeps going up. The logistic model, at a certain point, will actually start to level itself off in this manner, and will actually continue along some kind of a horizontal asymptote up here. Whatever this value is up here, it's going to level itself off. The value up there is what is called the carrying capacity. So the idea is something is going to grow exponentially for quite some time until it gets to a certain point. At that point, it's going to shift because you're going to start running out of resources. So therefore, the things that are growing exponentially, therefore, cannot continue to grow at that rate, and they start to level themselves off at what is called a carrying capacity. You can actually technically exceed the carrying capacity for a small amount of time, but eventually it's going to dip back below the carrying capacity. I'll write the equation down. Again, this is not something that I'm going to put in any of your problems, so it's not something you have to know right now. But the exponential growth and the logistic growth model is P of t equals C over 1 plus A times E to the negative KT power. The A is something we hadn't learned anyway. K still stands for the growth rate. T is still the time. The C is the carrying capacity. So if you actually want to know what this thing will approach and level itself off at, if you ever get this equation, you would know, oh, it's just that numerator. That's the C. That's the carrying capacity. So if you think about something like, you drop a population of wild animals on an island with only a certain amount of food, they may repopulate for a while. They may actually exponentially grow themselves for a while by, reproducing. But after a while, with a limited number of food, that's going to start to level itself off to a point where they can only withstand a certain amount of animals. So they'd have to level itself off. It wouldn't be able to grow exponentially anymore because you wouldn't have enough food. Anyway, that's the logistic model. That's all I'm doing with that. And I think we're going to go ahead and finish this video at that point. That finishes off Unit 7. So please make sure that you have all of this completed by the Tuesday that we come back. And I will see you all in class on that Tuesday. Have a great Thanksgiving.